All right, so we'll start out doing some Excel work. I'll kind of revisit what we worked at on the end of last week. So the very first kind of slide here is some stuff that we're going to do in Excel, and then we'll move on to the next kind of topic. So last week, I also kind of put up a connect assignment. So after, today, probably will get us so you could go through a little bit more than half of that connect assignment. And then by the end of the week, you should have everything to kind of complete the entire thing. And that's due next Friday at the end of the day. So you've got quite a bit of time to work on that. Any questions from you before we kind of jump into things like housekeeping stuff? Okay. All right. So let me go, before we go into Excel too much, I want to kind of revisit the general idea of what we were doing last Thursday. This pulls up here. There we go. So what we were starting out with was that we had some random variable x that was normally distributed. We knew its mean, maybe we knew its standard deviation. We're then saying, okay, there's some value. I think we're going to end up using 3 inches of rainfall because we're going to be looking at some rainfall data as the cutoff. And I want to know what's the probability I saw 3 inches of rainfall last year or anything below it, right? So what we were doing was we would use the z-score equation to convert whatever value for x we were interested in into a z-score, right? So this was like the z-score that kind of we turned 3 into. Then we could go to our standard normal table that we had started using, and it would tell us the area to the left, right? Or the probability of seeing that z-score or anything below it. Or the probability of seeing something this many standard deviations away from the mean or anything further below it. Okay? So that was kind of the general setup. So I'll try to, actually I'll move the marker. I'll keep this up in the over screen here. Let's see, I probably have to hit this one more time. And then we should be able to see this Excel document. So let's go blow this up a little bit. Okay. So I've got the work already done over here, but I'm just kind of delete this and show you how we could recreate that. So I'm going to delete that. I'm going to delete this. Okay. So up here is just pretty easy. Really what I had here was the mean, right? We could calculate the variance, and we could also find the standard deviation, right? Pretty easily, okay? So get rid of this for a second, but I'll bring this back. Here I've got kind of annual monthly rainfall, right? So if I want to look overall, kind of what's the mean monthly rainfall over the past, however many years, 100 plus years of data I have here. I'll select in that very first cell, then Control Shift or Command Shift on a Mac, hit the down arrow, hit enter. Now I've got my mean. I can find my variance by simply, this is population data. This is every year we had data on for Indiana. So over this time period, we have population data. So I can select that column again, hit enter. Now I've got my variance, right? And the standard deviation is simply the square root, right, or SQRT function of the variance. So I could do that pretty easily. Now I broke it down here by months, right? I think, let me see, I've got a time series, where is it? If we kind of look at monthly rainfall, it looks pretty normally distributed. Sometimes, depending on where we the histogram, it looks a little bit maybe like it's skewed, but for overall monthly rainfall, this is a pretty nice normal distribution. Okay. So go back to that rain worksheet. I could also break this down by month. I could find the mean using the average function. If I scroll over here, notice I've got every single different month. So I'm just going to select June, Control Shift or Command Shift on a Mac down arrow, hit enter. Now I've got my mean kind of rainfall for June. I can do the variance. So scroll back over here, select that variable again, and then the square root of the variance. That would be my standard deviation, right? So that's how I could kind of recreate that, right? This is stuff we've already done. Hopefully that looks pretty easy. But notice, when I was looking at the mean of column H, that was June. Well, if I have these in order, June, July, August. When I copy these functions over one, column H will become the next column, which would be column I, right? Which would be July's temperature. So I can get the mean, the variance, and the standard deviation of those kind of 4 months pretty quickly. And I could do this for all 12 really if I wanted to. It's just that 4 kind of shows up a little bit easier here on the screen. I then might be interested in different cutoff values for each month. So I just put some values in here. So that's why on the what I was drawing, right, I was saying, well, what if we had 3 inches of rainfall and wanted to know what's the probability I see 3 inches or fewer, right, this June? Well, to get the z-score, right, that was simply where we take, and see if we can work along here, the x value we were interested in. So the x value we're interested in was 3 inches, minus that mean June rainfall, which we had up here, and then divide by our standard deviation. So that would give me, that would kind of transform that x value into a z-score. So I'll hit enter there. I get a z-score of about negative 0.78. Right? So if I'm thinking about what we just found here, I could then look that z-score up on my table and I could find the area to the left. Well, instead of using the physical table, right, I can use this norm.s.dist function in Excel. Norm.s.dist tells Excel, hey, I want you to use a standard normal distribution, look up this z-score, right? So I click on that z-score, and then comma, do I want it to be cumulative or not? Well, here's just kind of a weird thing that's built into Excel. If I put, technically, if I think about the probability density function, what should the probability of any one value be? Yeah, we said it was going to be 0, right? The probability of any one specific value is 0. So it doesn't make a lot of sense for us to use that. We're always going to be using this cumulative option of the formula, which is comma 1, right? Find me the probability of seeing this z-score or anything below it. Okay. So this basically works just like the table, right? If I hit enter here, I get about what, 0.2168. If I pull open my standard normal distribution table and I look up my z-score of what, negative 0.7, and I have to remind myself where the 8 column is, so I scroll up. That's the second to last, so negative 0.78 is about 0.2177, right? Which, pretty close to this, right? But it's going to be a little bit off because I had to round that z-score to the second decimal. So in Excel, we can actually get even more precise, right? We don't have to round our z-score to the second decimal. Basically, when I say it's like Excel's using the table, it's actually integrating the function. So it can really do the math for us and come up with that area to the left very precisely. Okay? But essentially that 0.21, that's that shaded area we were looking for. Okay? Now I also can use a norm.dist function. So this doesn't have the .s in the middle. So this says, well, we're not using a standard normal distribution. I'm just looking at a normally distributed variable. And the cutoff value I'm interested in is x, right? Or here our x is 3, comma, what's the mean of June rainfall, comma, what's the standard deviation of June rainfall, and then comma, do you want it to be cumulative? Well, yeah, we're looking for the area to the left. We want this to basically work kind of like our standard normal table. Now, what this will do is it takes that cutoff value for x, the mean and the standard deviation, and it calculates the z-score behind the scenes. So we'll never see the negative 0.78 if we use the norm.dist, right? It calculates the z-score behind the scenes, then looks at that z-score up in the table, returns you the area to the left. So it should be the exact same thing as if we would have used the other approach. So it's 2 different ways of getting at the same thing. Here, you get to kind of see the intermediate kind of z-score value. Here you don't, so I always kind of call this as more like black boxing, right? You kind of don't know what's going on in the box. I'm using this, norm.dist function, and it's calculating the z-score behind the scenes. It's looking it up or integrating that function and returning me the probability or the area under the curve up to whatever that cutoff score was for x I was using. Okay. So kind of just a reminder of the order there. It's kind of small here, but the first thing you put in the norm.dist is that cutoff value for x you're interested in, then the mean, then the standard deviation, and then comma 1, making it cumulative. Okay. Any questions on any of that before we keep moving here? Okay with that? So if I highlight these and copy them over, it'll basically just grab the mean and the standard deviation of these different months, right? And so I could start to play around with cutoff values. You know, I don't know, what's the probability we get 4 inches or fewer this August, or 1 inch, right? We could play around with these different cutoff values and get the probabilities pretty quickly of seeing that little amount of rainfall. So you can imagine, like, anything that kind of hinges on rainfall. This is a very practical application of this. But what I'm going to change to instead, so that's kind of, I think, not too bad. We want to do this here. I'll wait and do this on the temperature one. So let's say we go to that temperature worksheet instead. So I'm going to zoom in so we can see this. I basically have the same sort of setup, except I did it for 3 months, right? And I kind of have, you know, you could use the norm.s.dist or the norm.dist function, you know, depending on what you want to do. So what if instead I wanted to find the probability that, x is above a certain value, right? So instead of being below, I want to see, is it above? What could I do here? Well, if I know the area to the left, now I want the area to the right. Yeah, right? Simple as 1 minus that probability x is below whatever x value we're looking at, whatever. So here, 71.4. That easy, right? I could have also, I didn't have to do this in parts, right? I know I wanted to take 1 minus the probability that it's less than 71.4 here. So I could have put that norm.dist function. Here's my cutoff value. I'm interested in finding the probability of it being above. So I have to find the probability of being below it and subtract it from 1. Comma, here's June's mean temperature, comma, here's the standard deviation for June, comma, make it cumulative, right? So this function will return me the area to the left of 71.4, and then when I subtract it from 1, it gives me that area to the right. So I can do it all in one cell if I want to, or I can break it down into parts. It doesn't really matter. What if I wanted the probability that I'm in between two values? So let's say the temperature of, I don't know, 70 and 72, right? So what I'm looking for there, what was the mean? I think the mean was like 70.75. So I'm looking for what's the probability in between 70 and 72. Right? Well, what I can do is I can use those norm.dist functions. I'll find the area to the left of 70, subtract that from the area to the left of 72. If I subtract this kind of green area from the blue area, I'm left with what's in between the two. Right? Or think about really what I'm doing there. That blue area represents the probability that I see x be less than 72. I only want the numbers between 70 and 72. So I need to subtract from this all the values. Oh, sorry. Oh, I see. Sorry. There you go. Thought you meant the screen and switch over. So if I've got the probability of being less than 72, right? That's kind of that blue area. What I want to subtract from it, right? I don't want anything below 70. So I'll subtract the probability that x is below 70. Well, this is essentially just turning those two values into z-scores, finding the areas to the left of them, and then subtract that smaller one from the larger one. Right? So if we take every number below 72 and then subtract out the probability of every number below 70, what I'm left with is just the numbers that are in between. So if I want to think about what this looks like in Excel, let's do, I don't have the equals to signs on here, which isn't a huge deal because we said the probability of any one specific value is 0, so that shouldn't change our answer much or at all. So I can use that norm.dist function. My first cutoff value I had was, well, I want to go up to 72, comma, here's the mean June temperature, comma, here's the standard deviation. I want the entire area to the left, so comma 1 there. I then could subtract from that the norm.dist function where I'm looking at the kind of plugging in that lower value, because that'll give me the probability of seeing 70 or anything below it. So comma, select the mean, comma, select the standard deviation, comma 1. So really this is telling me the probability of being below 72, subtract from that the probability of being below 70, so that just leaves me with the values that are in between 70 and 72. Okay. Any questions on this? Yeah. S.dist? Yeah. So the norm.s.dist, right? The only reason you should be using that is if you already have the z-score or you've already calculated here, right? Because when you're telling it a value, it's treating it as though it's a z-score. So it's treating it as though the distribution has a mean 0 and a variance of 1, right? The other one, norm.dist, treats the mean and the variance as whatever essentially you tell it here. I mean, probably in practice, it makes more sense to do norm.dist because it's just a little bit less work, right? You don't have to manually calculate the z-score. Now, if you have a bunch of z-scores and you want to know the area to the left of them, then you have to use the, well, technically you could use norm.dist and plug in the mean 0 and variance of 1, but yeah, if you have a z-score, you're best off using the norm.s.dist. And we'll start using that one a little bit more once we're thinking about like confidence intervals and things, but that's a little bit further out. But that's why I'm introducing, so even here, even though here it doesn't make as much sense to use this, we will be using it in the future more, so that's why I'm introducing it now as well. Yeah. This one? Yep. So if it helps to like make this look a little easier, anytime you see this norm.dist, we're always going to be using the cumulative option, this comma 1. So you can always think about all the norm.dist is telling you is the area to the left of whatever value you've plugged in here first. That's really all that norm.dist. You could almost, you could replace it with the probability x is less than or equal to 72. That's all that first norm.dist is really giving you. Okay. All right. Any other questions? Nothing in the chat. All right. And we could copy this across and we could do this for oh, if I can grab this right. There we go. Do it for different months and play around with these cutoff values, but yeah, that's the general idea. Okay. So let's go to this inverse transformation sheet now. So once again, I'll give you kind of a review of what we were doing last class. So where is it? There we go. So what I drew for you earlier was this idea of we're taking, so what we were doing before was we were taking an x value, we were turning it into a z-score, we were then looking that z-score up to find the probability of seeing that value for a z-score or anything below it. When we worked with the inverse, what that was doing was saying, well, look, now I know the area and I want in the tail, maybe it's, I don't know, 0.2. What z-score would give me 0.2 in the tail? Once I have that z-score, we had this inverse transformation formula, which was really just rearranging the z-score equation to solve for x. Well, now that I have the z-score, if you tell me the mean and the standard deviation of the original distribution, I can back out what that cutoff value for x would be that would give me that 0.2 to the left of it, right? Or the probability of seeing that value or anything below it would be 0.2. So we're now starting out with a probability and working backwards to find that cutoff score. Okay. So the example we did last Thursday, kind of just to revisit it, and we can see how we would have done this in Excel. I had a test score that had a mean of 72 and a variance of 64. So I'm going to delete these because I'm going to rebuild them and show you a few things. So let's say I wanted to find the test score. That would be the 90% cutoff, right? Or the test score such that I'd be in the top 10%, right? Above 90% of the other test scores. So what I'm going to do is use the norm.s.in. Well, actually, I'll show you using this one first. Let's just use the norm.inv. Okay. So norm.inv, you tell it the area you want in that left tail. So we wanted that 90% kind of cutoff where I'd be better than 90% of the other test scores, so 0.9. Comma, what's the mean of that distribution, right, that normally distributed variable? And then what's the standard deviation? Well, if I select the variance here, that's going to be a problem, right? Because it needs me to tell it the variation. So the standard deviation. So if I tell it the variance, notice I get that 154 on this test would be the 90% cutoff. Well, if the average is 72, I mean, this is a normal test, 150 out of 100 doesn't make a lot of sense. Well, the reason why is because I put the variance in here. I have to tell it the standard deviation, so I need to make sure I take the square root of that variance. Okay. Now I could have done this in a separate cell, like calculated the standard deviation here, inserted another row, but I can do this all in the same kind of function by just taking the square root of the variance here, because this norm.inv needs the standard deviation. Okay. So if I hit enter, it tells me that the cutoff score for the 90th percentile is about an 82.25, which is the same thing we found last week by hand. Okay. Now, what we could have done, right, is first found what that z-score is. So what Excel is doing, is kind of looking up this area of 0.9, finding the z-score that corresponds to that, plugging it into this inverse transformation formula, using the mean and the standard deviation you told it, and then spitting out at you that cutoff value for x that would give you that desired 0.9 in the tail. Now, it didn't show you the z-score. You could have calculated it kind of on your own. So if I know that I want 0.9 in the lower left tail, if I use the equals norm.s.inv, and I tell it the area I want in that lower left tail is 0.9, when I put the .s in here, just like with the norm.dist and norm.s.dist, it now tells us, okay, this is a standard normal distribution. What value, what z-score from the standard normal distribution would give me not 0.2 here, but 0.9 in that lower left tail? Right? So it'll spit out at me that z-score of 1.28. I could then manually enter in this inverse transformation formula where I say, okay, this is going to be the mean plus that z-score that gives me the desired alpha in the tail times the standard deviation, so the square root of the variance, right? Now, this should be the exact same thing I got before. Sure enough, I get the same thing. It's just I did kind of one more step here, which is I found the z-score first and then plugged it in myself, right? Here, just using the regular norm.inv, kind of Excel did all that work for me. Okay, so this is probably the easier one to use in this situation. Right? Any questions on that before we keep moving? Okay. Now in practice, probably what's better to do, instead of entering that value in here, I could like put it over here in a cell. So now if I want to find the cutoff for the bottom 40%, it'll give me that test score. And I could go, what about the bottom, 25%? And I could play around with it and change it a lot easier. So probably using a cell reference is better in practice, but I wanted to show you kind of having a number there, right? What that was representing. That first number is the probability or the area that you want in that left tail. Okay. Any questions on this? All right, I might show you, I'll show you this kind of at the end of class just to highlight some things we could do in Excel. So let's go back. We're going to take kind of a veering off from what we've been talking about, but we'll return to it soon enough. So where we're at to this point, when we're talking about these normal distributions, we're talking as though we have the population data. The problem is population data is really hard to obtain. So actually, I'll switch this back if people want to see me talk, they can, I guess. So we could have two different types of population data. One, a finite population. I mean, even something like the US population, right? It caps out at 300 something million, right? So there's, even if it's really large, it can be finite. And we can look at infinite populations, usually from some data generating process that's just going to kind of continue off into eternity, right? So this isn't a big deal that we make the distinction between the two. We're going to treat them very similarly. One thing that we often don't have, though, is we don't have the actual population data, right? It's not very feasible to take a census. We've already talked about this before. So all we have to do, we have to resort to a sample and make inferences about the population using the sample. Okay? So don't worry too much about this if you're kind of jotting things down. I'm going to go away from it, but this isn't too big. It's just kind of setting things up. So when I take my sample, we're going to call the size of that sample lowercase n, and the size of the population kind of capital N, right? So we had a little bit of this when we were talking about like calculating means and variances. Capital N is the size of the population. Lowercase n is the size of my sample. Okay. So the main goal of all this is to get a sample that is as representative of the population as I can get, right? If I take a sample of 100 people and they're all over the age of 70, that's not going to allow me to make a lot of statements about the general population, right? Because I know that that age distribution of that sample looks nothing like the age distribution of the population, right? Not everybody's over 70. So what I can do or first, I can do things with or without replacement. So the idea of with replacement would be if I had, everyone's name in this class in a hat, I start pulling out names and recording that person's age. Maybe I'm looking at the average age or something. So let's say I take a sample of 10 out of the 40 students in this section. Well, if I draw out one name, I write that person's age down, and then I put that name back in the hat, that's with replacement. So what's one possible, if I don't, if I draw that name, write the age down, and then I kind of throw that name to the side where I can't draw it again, that's without replacement. So what's kind of one problem maybe if I use with replacement? Yeah, I could draw the same person twice, which now I have a sample where one person is carrying twice as much weight as everybody else, right? Well, that doesn't make a lot of sense. So 99.9% of the time, we should be using without replacement. I mean, there are some situations, depending on what field you're in, I'm sure where it makes sense to maybe do with replacement, but for us, more often than not, without replacement is going to be what we prefer. Okay? We need to make sure that these will be things that are always typically met, but we have to be cautious of looking at data sets that each element or observation should come from the population, right? If I'm interested in the average U.S. income, I don't want to have a Canadian in my data set, right? Because they don't influence it all. So that's one. The second is make sure that these observations are selected independently. This one usually only gets broken if we're being lazy, right? And doing something like I finally get someone to answer my phone call and take my survey, so I then ask if there's anybody else in the household that wants to take it as well, right? Because I know maybe now that I have someone on the phone, it's easier to do that. Well, the problem is the people in the same household likely have more similar characteristics, and so now these aren't independent. So that one's usually pretty easy for us to kind of sidestep that as well. So now we get to kind of talking about two strategies that we might need to employ to make sure that we're eliminating some biases that might exist. Okay? So the first was we're going to talk about stratified random sampling. Okay? So the idea here is that we have some characteristic in our data, right, that is like correlated with the statistic we're interested in calculating. So, and if my sample doesn't look like my population in terms of that characteristic, I'm going to have very skewed data. So I think the easiest one to think about is maybe I'm looking at the average height, right? And if I end up with a sample that has 80 males and 20 females, what do I know about that sample mean I'm going to find relative to the population mean? Well, I know that the population is roughly 50-50, right? Maybe a little bit off of that, but if my sample has 80-20, 80% men and 20% women, and I know that that characteristic of gender may be linked to height, well, yeah, now my sample mean is going to be a lot higher than probably what the population mean is, right? Because I have characteristics in my sample that don't match up with the population. So maybe what I do is I'll divide kind of my overall population into groups that are non-overlapping. So then what I'll do is from each one of these groups, these strata, I'll select a random sample. So maybe I separate my kind of population data up into males and females. I then select 50 men, 50 women. With those random 50 men and 50 women, I then put them in a sample together. Now I have a random sample of size 100, but I've guaranteed that the kind of gender breakdown looks similar in my sample to what it is in the population. And, you know, we could use a ton of different examples for this. Yeah, so once I take the sample, I put them all together to get a full sample. I could do this on several different things like age or income. So maybe I say, you know, I want to make sure that I have a sample. Maybe I don't know off the top of my head what age distribution looks like, but maybe I want to do something like, you know, I'll take 10 people from the age 0 to 10, 10 people from the age of 11 to 20. But now I'm going to take 9 people from the age of 21 to 30, and then 8 people, because I know that as I get older, I'm going to see fewer percent of the population be in those older categories. So once I kind of take those random samples from each age grouping, I would then throw them all together to get my full sample. Now I have a random sample where the age distribution matches that of the population, right? The age distribution in my sample, okay? So, you know, we do this a lot of times when we want to ensure that one group isn't kind of overrepresented. Cluster random sampling is the exact same idea, but instead of separating them into non-overlapping groups, we separate the population into like subpopulations. So usually this is done by geography, right? So maybe I want to have, maybe, I don't know, I'm interested in like which way the, I don't know, Senate's going to vote. And so I will just like survey the constituents to see maybe what the different states look like on a particular issue. So maybe I go to every state and I say, I want every state to be equally represented in my sample, right? I could then go to California, randomly sample 2 people. Go to New York, randomly sample 2 people. Go to every state, randomly sample 2 people, then throw them all together, 50 states, 2 people, I'll end up with a sample of size 100, and I know that every state would be equally represented in that. Right? Or maybe I don't do it by state, but maybe I do it by, oh, where is that? Here you go. I'll come back to the other slide. Maybe I do it by region of the country, right? If I'm trying to do some type of estimate on political polls, maybe I divide the country up into like 6 or 7 different regions. I then randomly sample maybe 20 people from each region and then throw them all together to my full sample. So now I make sure when I'm looking at these kind of, the polling data, I have every region of the country equally represented. And each region is really just a small kind of subpopulation of the whole population, of the whole population of the United States. So it's the same idea, right? I create these clusters. It's just that they're not being kind of separated by a particular characteristic like income or age. It's just more linked to kind of geography, right? But other than that, cluster and stratified random sampling, pretty much the same idea here. Okay? And I'm not going to make you kind of go out and do this. I'm just mentioning it so we can start to think about, this is one way we can start to eliminate some biases or kind of make sure our sample matches up to our population. Okay. So it's not very feasible to do the census. We're stuck with this sample. So what else do we need to worry about? Well, we'll go through this example, which is the 1936 presidential election, to kind of highlight a couple of these biases, because someone wrote a paper on it that allows, I think, is a good way to understand these 2 biases. So in 1936, Alf Landon was running against FDR. I mean, I'm not much of a history buff, but I know we never had a president named Alf. So, we know how this turns out, right? However, the Literary Digest, prior to the election, did this poll. So there's this Literary Digest, like this little magazine. I remember my grandma used to have a bunch of these old ones, but they sent out 10 million survey cards, right? And they got 2.5 million back. So I don't know what other classes that you've had, or if you've ever talked about like surveys or how to conduct them. A 25% response to mailings is really good. Like, they were probably very excited about this. We got 2.5 million responses. That's our sample size. That's huge, right? So they're like, well, with these 2.5 million responses, we can predict the election, right? That's a large enough sample. We should easily be able to predict what the outcome of the election is. So they look at all the results, and they kind of saw, where they sent the cards to, so they could break it down by electoral votes as well, and got a pretty big victory predicted for Landon, right? Now, we all know how it turned out. Roosevelt won, but what I didn't kind of realize is how many votes he won by. So, right, not only did the predicted landslide not occur, there was an even worse landslide in the opposite direction, right? So they got this very wrong. How did they do that, right? Math errors, were they using the wrong formulas when they were calculating and making their predictions? Well, no, right? But what's maybe a little more practical is, well, what if they only sent 10 million surveys out to only registered Republicans? Well, I know that at any one point in time, the country swings a little bit to, one way or the other, but it's usually around 50% kind of on the right, 50% on the left, right? That's why we have, continually see the political party in power kind of change, right? Because we kind of like this pendulum swinging around 50%. So if I had only mailed these to Republicans, well, I know that my sample is not going to match up with like a 50-50 split country population, right? So maybe they sent only those cards to Republicans. Even if they were able to send 5 million to registered Republicans, 5 million to registered Democrats, what if the Republicans were just more likely to respond? So what if of the 5 million they sent out to both parties, 0 came back from Democrats and 2.5 million came back from Republicans? Well, that would cause us basically to have the same problem. Now I have a sample that's just full of Republicans and not a 50 split like the population. So these two things are instances of two general biases that can often occur, especially when we're looking at survey data. So the first is a selection bias, right? If I over-selected a certain group to get those survey cards, right, I only sent those cards out to Republicans, then I was creating a selection bias. I was having kind of a certain group either be overrepresented, which would mean the other group ends up being underrepresented in my sample, right? So that's my selection bias. If I'm over-selecting, right, from a certain group to be in my sample. The non-response bias would be, well, even if I'm ensuring that I'm reaching out equally to these different groups, if one of them is more likely or less likely to respond to me, I might have a non-response bias, right? If the Democrats didn't send any of the mailers or the survey cards back, well, that's a non-response bias. And those are a lot harder to fix, okay? But we'll see why the selection bias, specifically in this case, could have easily been solved. So what the Literary Digest did was to get the names to send these survey cards out to. It had this database of individuals who were cross-listed between telephone books and car registrations. So the only people in that database owned both a car and kind of had their own telephone, right? In 1936, who had both of those things? People that had, who owned cars in 1936? What end of the income distribution? The right end, right? The high end, right? So we had mostly, right, we oversampled or over-selected wealthier individuals, right? When we look at higher income amounts, specifically like the top end, we tend to see that voting records go more towards the right, right? You can probably imagine most of this is probably driven by taxes and not wanting to pay a lot, right? So if we oversampled from the wealthy, who we know on average vote more towards the right, we really did over-select Republicans here, right? So our data is going to be skewed to thinking the Republican candidate, Landon, was going to win, right? So what these researchers did was they tracked down a bunch of people who actually voted in the 1936 election. And I forget when they did this. Like the people would have been fairly old when they were kind of collecting this data. And they asked them, who did you actually vote for? And at the time, did you own a car and a telephone? Did you own a car only? Did you only own a telephone, or did you have neither? Right? So they end up with about 2,300 people in their sample. And when you look at it, people who own a car and a telephone actually did vote about 53% for Landon. So the Literary Digest poll wasn't off by that much if you're basing it only off of people who own a car and a telephone. If they would have simply gotten names, not from a database where it was cross-listed, but where people only had a car or only had a telephone, they actually wouldn't have had a problem, right? They would have actually made the correct prediction because 60% of people in those categories actually ended up voting for Roosevelt. Right? And then if they would have been able to get people with neither, hell, 73% of them voted for Roosevelt, right? So, you know, because of the method they used to get the names to send these mailers out to, they were doomed from the beginning trying to make this prediction, right? Because they only had people who owned a car and telephone in their sample. And that didn't match up with, if we look at the population, right, the kind of total of these four categories, that doesn't match up to the population at all, right? Where about 60% of people ended up voting for Roosevelt. Okay. Any questions on this before we keep moving? So this really is highlighting our selection bias. We over-selected from this group. What about a non-response bias? Well, I mean, we had 25% of people respond, but what if Republicans, for some reason, were more likely to respond to this survey card? So the paper tries to explain this. I don't really buy it too much, but their idea is that potentially people that have higher incomes could be even more likely to respond to these surveys because they have more time, or they can be more politically involved than if you're kind of on the lower end of the income distribution, right? You're fighting to survive and you don't have time to worry about sending a mailing card back. But when we look at this, you know, in every single one of these categories, doesn't matter if people had neither a car or a telephone, only a phone, only a car, or they had both, for whatever reason, that when they went back and looked at who returned this poll, right? All the numbers, right? So if I look at people who owned a car and a telephone, for some reason, 16% of people who ended up voting for Roosevelt sent it back, while 35% of the people who ended up voting for Landon sent this card back. And then same kind of thing, car only, Landon voters responded to this poll a little bit higher, telephone only would have been more likely to respond to the, you know, so it's like, no matter what they would have done, for whatever reason, the Republican kind of candidate at the time, people were more likely to send in that straw poll or more likely to return it. And maybe this was because, you know, more people were just undecided, right? These definitely don't add to 100%. So there was a lot of people who just, you know, weren't, you know, sure who they were voting for. So they probably didn't return that straw poll. But here we can see that for whatever reason, there was a non-response bias as well, where people who were going to vote for Roosevelt were less likely to send this survey card back. Okay. So what else can go wrong? You know, people can lie either maliciously or non-maliciously. That can cause biases. We see this a lot of the times. Like if you ever ask any questions about drug use or like alcohol use, it's always well below kind of like the clinically reported amounts or kind of looking at just sales. So people might, you know, not want to respond to certain questions, so they'll lie to you. Some people non-maliciously lie, right? If you ask me exactly, you know, what my income was last year, I'm probably not going to be able to give it you down to the cents, right? I'm probably going to round it. I'm not maliciously lying to you, but I am giving you technically a fake value. Right? It's close to the real value, but it's not completely 100% accurate. Right? Sometimes people just don't understand the question, so there's a lot of literature out there right now or research looking at people respond differently to different phrasings of like the same question. So I remember I saw this poll, this is before the last election, something about like, do you approve of something Donald Trump is doing? But they phrased it in two ways. And they got something like 40% were in favor on one, but like 65% were in favor. But it was really just asking the same question, just in a slightly different context. So even how you understand the question can elicit different responses, right? It can cause some bias. So we'll go through a couple examples and think about some of this, some of these different biases that could exist. So let's say, you know, an example I'll give, well, let's say I asked, how would you rate your health from 1 to 4, right? Say we had a room full of people and we asked people this, right? Well, some biases that could exist here. First of all, just the understanding of the question. I might look at this initially and think, oh, 4 is the highest, so I feel good, I'm a 4. Well, 4 was actually right from 1 to 4, but 1 was being kind of the best. So I could just misinterpret the question, especially a question where you're using numbers to represent like how someone feels. What's a non-response bias here? So who do you think would be the people who would be most likely to not respond to a question like this? Well, younger people potentially. Like if I had like a group that had a whole age, you know, varied in age, maybe I have people at the young end who don't want to respond. But if I just think about something that's related to this, I mean, if I'm in good health I'm probably not that worried about telling someone I feel like I'm in good health. If I'm in poor health, probably a little bit more likely I don't want to respond and tell someone I'm in poor. So the non-response bias we could get here is probably coming from people who are not as healthy, which then could, if we look at our sample, we're going to think that if we're trying to make inferences about the population, that the population is healthier than it is. Because the people who aren't responding were ones with lower health. Now, you're right. If I'm thinking about like doing this survey on a larger scale, I'm probably getting higher responses from older people versus younger people. I'm probably getting higher responses from all types of things, but kind of specifically thinking about just related to health, who would be the non-responders. Let's say I asked, another issue could be, what if I asked this question, like usually when everybody's in person, I would use like an iClicker to ask this, and then we would look and see like someone answered a 4, and usually someone says, no, I thought it was a 1. And so it really highlights the fact that like misinterpreting the question can cause issues in your results. But also, if I only asked this course, maybe it was part of the online quiz, what would be an issue with kind of gathering this data from you guys and then making inferences about the population? What should be hopefully true about your guys' health relative to the population? Probably better than the average, right? Because you've got a lot of 70-year-olds in the population, right? So, I would have a selection bias. I over-selected from a certain age group if I just asked you guys and then try to make inferences about the population. Another issue that questions like this we always want to think about, but people often don't maliciously lie to you, but if we look at a lot of the research out there, people usually underestimate what their health level actually is. And so that would be a bias that exists. We already talked about the interpretation. I haven't talked about this one yet, but if I kind of forced you to give me 1 through 4, well, if I feel like a 2.5, what do I answer, right? So if we force it to be discrete, we're almost forcing people to like somewhat non-maliciously lie to us, right? They feel like a 2.5, but you're forcing them to tell you either a 2 or 3, so they're giving you incorrect data in a sense. The other one, if I asked you guys, like let's say I did this on an online quiz, how many alcoholic drinks do you have an average every week? Don't worry, I won't do that. But what are some biases that might exist there? Well, first of all, what's the selection bias? So I'm asking you guys, relative to the population, same kind of thing with health, except for it goes in the opposite direction. You don't have better health, you have worse drinking habits, right? So you're younger, relative to the population, I would expect there to be kind of this upward bias here, right? That I'm going to see a higher average from my sample of people in college than I would for the population as a whole, right? What about a non-response bias? Well, there's a couple different kinds of non-response bias that could work here, but the main one is people who aren't 21 are definitely, might have a lot more of a reason if they think I'm going to collect this data on Canvas and do something crazy and get you in trouble, right? Maybe I just don't want to respond, or I respond with 0, right? So that's going to push my results down, right? Or maybe people don't want to kind of admit to maybe drinking as much as they do every week. But then again, maybe I have kind of an over-response bias where people are, the one guy at the party who always wants to kind of tell you he's drinking the most, right? So I've got biases that can work in a lot of different directions. If I'm just asking a question like this, I want to try to strip down as much as I can any concerns from the person about me saying this. Like, so a lot of the times you'll get these surveys, they make sure that it's anonymous. No one actually sees your name or ID number or something associated with these different responses, because otherwise all these different types of biases could exist, right? But if no one's ever going to know it's you, you're a lot more likely to get some truthful responses. Yeah, these are just, we've already kind of covered these and some other ones. So I just like thinking through these to understand whatever data set we look at, we're probably going to see a bias. So I usually would go through this, but I don't know if I feel like it today. I think, where are we at in time? 25 minutes? Maybe I'll revisit this next class on Thursday just so we get another discussion of bias and we get it on 2 separate days. But it's kind of interesting, but there's a paper that goes along with it. I want to spend a little bit more time if we talk about it. So we'll kind of revisit this idea of the bias existing in our sample in terms of the elections and a kind of a paper that was written on it. But I do want to make sure we get some kind of discussion today about the distribution of sample means. So all this discussion about these biases that could exist, we're really building us up to, okay, if we're aware of all this and we've tried to eliminate as much as we can, so we get a sample that should be very representative of my population, right? I've eliminated all these different biases that might exist to the best of my ability. What's going to be true now about the statistics I start calculating using those samples? So once I have my sample, right, let's say I did, I don't know, sampled 100 people and I calculated their incomes, right? I could find the sample mean income for those 100 people. Right? Now, what do I know is going to be true about this sample means that I see? Well, look, if I take a sample of 100 people randomly and I eliminate all my biases, what are the likelihood that for those 100 people, the average income is 200,000? That seems like it would be relatively unlikely. I mean, for 100 people to have an average income of 200,000, if I truly selected them randomly from across the entire population, I mean, the average income in the US, I forget exactly where it's at. I think it's somewhere, well, we can look it up so we can actually have some numbers that have some meaning to it. So average US income. It's about 31,000, right? So if the average is 31,000, how likely is it that I see the average of 100 people be 200,000? Almost impossible, right? I'd have to have a bias that existed there. How likely is it that I see, if the average is 31,000, how likely is it that for my sample, I see a sample mean of 35,000? Well, it's not equal to the population mean, but if I randomly sample 100 people and I end up with one or two people that have higher incomes, that's very plausible for me to see an average income of 35,000. So we know that there are going to be certain values for that sample mean that are more likely than others, right? And the ones that are more likely, right, are going to be the values that are around the population mean, right? I'm more likely to see values for my sample mean around whatever that population mean is. And then as I look at values further from that, right, if I look at that sample mean income of 31,000, if I look at that population mean income of 31,000, as I get further from that, right, I start to think, well, those values become less and less likely, right? By the time I get up to 200,000, I know that seems really unlikely, right? So the sample means are going to have their own distribution, right? Certain values will be more likely for me to see of the sample mean than others. Okay? What also ends up being true is if I take different sample sizes, the likelihood of seeing different sample means changes. For instance, if my sample was of size 2, well, now what's the likelihood I get a sample mean of 200,000? Well, if I'm randomly sampling 2 people, I could have just ended up with one person that had a really high salary amount, right? But with 100 people, how likely is it that I see 200,000 as the mean? Well, even if I get 1 or 2 people with really high incomes, that gets averaged out when I have a larger sample size, right? So taking samples of different sizes will also kind of influence this distribution. And we'll talk about how in just a second, a little bit more specifics. So, I can think about this distribution is going to look different for samples of different size, right? What ends up being true is that if I take a sample of size n, so sample size lowercase n, from whatever data I'm looking at, maybe looking at income, and I'm taking a sample from the population of the entire US population, I know that there does exist some population mean and there does exist some population variance. Even if I don't have the population data, I know they exist, right? What ends up being true is the mean of my sample means ends up being whatever the population mean was, right? So kind of think about it. Try to give a visual to this, I think. Start out a little slow here with some of this so we make sure we get a really good understanding because we're going to be using this stuff a lot. You can see it up there? Okay. So there's some variable x, all right? We'll use the income one, right? 31,000 was kind of the population mean, right? Okay. Well, what ends up being true is if I think about the sample mean values I could see, right? Well, the most likely values are going to be closer to that population mean. Right? It's going to be very, it's very possible if I'm selecting one person at random that for this variable of income, it's very possible I see like 150,000 if I'm just selecting one person. However, if I'm taking samples of size 100, how likely is it for me to see a sample mean of 150,000? Well, not near as likely, right? So the values that are like further from the mean become almost impossible for us to see when we're thinking about the distribution of our sample means. And then the values near the mean, right, are going to be more likely for us to see. Okay? But what ends up being true is, if I were to like say take, let's say I took 1,000 different samples, all of size 100, I calculated every single sample mean, right? So I'd have 1,000 different sample means. I could get a histogram, right, and draw out that distribution of those sample mean values. What ends up being true is, if I were to do that, those 1,000 different sample means, like I had them in an Excel file, if I took the mean of those sample means, so the mean of the sample means, it'll end up being exactly whatever that population mean was. And it kind of makes sense. Like if I'm sampling from this variable, then if the more likely values are going to be the values around the mean, it's more likely that I'm going to see sample means around that mean as well. And then kind of the values further from that population mean are going to become less likely. Okay. Now, if I take samples of size 100, here's another way to think about it. And I have income as the example here, but I think height, it's a little bit easier to think about with height. Let's say I took a sample of size 100 and I calculated the average height of that sample. Well, if I have 100 people, how likely is it that I see the sample mean be that they are 7 feet tall? I mean, that seems crazy, right? I don't even know if I could gather up 100 people that are 7 feet tall, right? So what if my sample was only of size 1? Well, now what's the probability I get a sample mean of 7 feet tall? Well, there are people that, if I'm randomly selecting one person, there is going to be a slightly higher likelihood that that one person is 7 feet tall, as opposed to the sample mean of 100 people being 7 feet tall. So the variance of our sample means is going to be related to the underlying variance of the original data, but as I take a higher sample, right, the variance is going to become lower, right? Those values very far from the mean are going to be very unlikely for us to see as a sample mean value with a sample size of 100. So the equation that ends up being true is that our new variance on the sample means will be whatever the original variance was divided by our sample size. So as that sample size gets higher, the variance on our sample means gets lower, and we can kind of guarantee, right, that we're getting more values right around wherever the true population mean is. Right? And you can think about it, really what we would like to do is look at our sample mean and be able to give a real high guarantee that this is going to be close to whatever the population mean is. How can I do that? Well, if I take higher and higher samples, eventually I end up with this like distribution that's like almost, right, all the probabilities of seeing those values really close to that population mean. So there I'm almost guaranteed that if I take a sample, I'm going to end up with kind of a value that's very close to that population mean. That's like our end goal. So with that being said, right, we've got the mean, and we now kind of have this equation for the variance of our sample means. Just the original variance of the data that we're sampling from divided by our sample size. Okay? And hopefully we kind of remember sigma squared here was the variance of the original x variable we're looking at. Okay? So not only, do we have this equation for the variance, I've kind of already mentioned this, but as the original variance of the data goes higher, so will the variance that we could see on our sample means. I think that just kind of makes sense. Like, if I was looking at taking samples of, U.S. income versus, I don't know, choose a country that has relatively low kind of income values overall. So maybe something like, Serbia or something like that, right? The variance on income in Serbia is going to be much lower. And so, if I look at samples of Serbian incomes, they're going to have, the sample means will have a variance that's much lower. So, those two things are directly tied. Now the sample size is kind of inversely tied. We already discussed that, where as I take higher and higher samples, that denominator gets larger, then I'm going to see a lower and lower variance on those sample means, right? Taking higher sized samples kind of reduces the variance on that distribution of sample means, guaranteeing that I'm more likely from this, red distribution to get values that are really, really close to whatever the true population mean is. Okay. We'll use the standard deviation as well. So one thing that ends up being true, if I take the square root of the variance here, so if I take the square root of the sample mean variance, I can write this two ways. Oh, I was going to say, I'm getting some looks, so I was guessing maybe something was going on. So I just talked through this and you guys didn't see it, right? But we already discussed kind of that sample size, right? As that denominator gets larger, it'll drive down the variance of my sample means. When we want to take the standard deviation of our sample means, if we take the square root of this variance, right, you could just write it as the square root of the variance like we have over here. Or I could simplify it to where the square root of something squared is just itself, and then we would be dividing by the square root of n. So these are the same, mean the same thing, right? Just kind of depends. If we're given the original standard deviation of the variable we're sampling from, this one's easier to use. If we're given the original variance of the distribution we're sampling from, this one's probably easier to use. Okay. And I won't ever kind of push this, but we need to make sure that we have kind of a large enough sample relative, we need to make sure that our sample is not too much of the population, but this should never be a concern for us, especially when we're thinking a lot about like the population of the US or the world or something. So how can we start to think about this with some actual values? So let's say I had, was this Indiana births in 2004. So I had this data set where I had every single birth recorded in an Indiana hospital. So you can find you've got population data essentially, right? So I could find the population mean pretty easily using the average function in Excel. I did that. Found the variance. I rounded it to make it a little bit easier for this example. But here I've got the original variable x. I know its mean and I know its variance, right? So if I take samples of size 36 and I want to find what's the mean, like if I take a sample of size 36, what's the mean of the different sample means I could see? Like, so let's say I sampled 36 babies, write that sample mean down. Randomly sample another 36 babies, write that sample mean down. Randomly sample another 36. I continue to do that. I then have like 1,000 different sample means. What does the distribution of those sample means look like? What is the mean of those sample means, and what's the variance of those sample means? So what we're thinking about here is I've got this original variable x, which was kind of birth weight, and it was normally distributed with a mean of 3,287 and a variance of 360,000, I think is what I said. So essentially what we're thinking about is there's now a distribution of sample means. If I take samples of size 36, they're going to be centered around, right, the mean of my sample means is whatever the population mean was, which here was 3,287. Right? Now, try to get this all in once. There we go. The variance of those sample means is just going to be whatever the original variance is divided by my sample size. Right? So the original variance divided by my sample size, that gives me the variance of my sample means, which here is what? I think it's, so about 10,000. Okay. Any questions on that? So this is kind of how we're thinking about mapping out the original variable into thinking about the distribution of our sample means, right? This was x bar, our sample means, okay? So the mean of our sample means was the original population mean of 3,287. Oh, and I wanted the standard deviation here, so I had to do one more step, right? I had the variance of 10,000, so I wanted the standard deviation, just the square root of that. Oops, just the square root of that 10,000, which should have been 100, right? So that's how we would have gotten to A here. Okay. Any questions on that? All right. What if I instead sampled 100 babies instead of 36? What's going to happen? Well, the mean of my sample means, what's going to happen to that? Yeah, it never changes, right? Doesn't matter what the sample size is. Yeah, it doesn't matter what the sample size is. The mean of my sample means is always whatever the original population mean was, so 3,287. Now, if I take a higher sample, right, I'm going from 36 to 100. So this denominator is going to go up, right, from 36 to 100. Without calculating it, if my denominator gets larger, what's going to happen to my variance? That denominator is getting larger, my variance is getting smaller, right? Higher samples, we can really narrow down where that value is at. So I know my standard deviation is going to be lower than what it was before. Right? My variance and standard deviation have to be lower than what it was before. So before it was 100, so now when I take samples of size 100, right, that higher sample, my standard deviation has to be above 100. The only options here are 600. And the mean of my sample means is that original population mean. So I know A is going to be the correct answer here. Right? Now, if I want to actually go ahead and calculate it, the only difference is I plug 100 in here instead of 36. And you will end up kind of getting that standard deviation of, oh wait, sorry, I said 600. That's wrong, right? The standard deviation is lower than it was before. It was 100 before, so it has to be 60. Sorry, I misspoke on that. So it's not A, the answer is going to be C, right? If I plug in 100 here, I get what? 3,600, take the square root, I end up getting at standard deviation of 60. Okay. All right. We'll kind of hit on this a little bit. But I've really been trying to hammer this idea already, but when we take these higher samples, that means I'm reducing my variance, right? So that denominator gets larger, the variance or the standard deviation is getting smaller, right? And it kind of makes sense. I've already tried to get at this idea of like, if I take samples of size 1, I can have a sample mean where someone's 7 feet tall. If I take samples of size 100, that's almost impossible. So these extreme values out here that are far from the mean are a lot more likely when I only have samples of size 1. As soon as I start to increase my samples, maybe go up to sample size 5, these values become essentially pretty much have a probability of 0 of occurring, and then the values around the mean become more likely. And if I go to an even higher sample, right, these values that are very far from the mean become pretty much impossible for me to see, but the values that are really close to that population mean start to become more and more likely. So higher sample sizes means we can really pinpoint down where this population mean is, even if we don't have population data and all we're able to see is the sample mean, okay? And also just intuitively, the more information you have, the better, right? So having a higher sample size means you're getting more accurate representation of where the population mean is. Now, we've already talked about this a little bit, but as I take higher and higher samples, right, I get this more. If the higher samples lead to lower variances or lower standard deviations, I'm going to end up with a more and more peaked distribution when I have very high sample sizes. So the sample size of 50, I get this really peaked distribution. Sample size of 1 is essentially this like squiggly line that kind of runs almost straight across. So higher sample size, lower variance on my sample means, and I can really pinpoint down where that true population mean is. So I start out, if I have a normally distributed variable, right, this variable x, it's normally distributed, it has its own mean, its own variance. And then I have my sample means. I know they will also be normally distributed, and their mean will be whatever the population mean was, and the variance of these sample means is the original variance divided by my sample size. Okay? So if I start out with a normally distributed variable, I know if I take samples from it, those sample means will be normally distributed around whatever that population mean was, and my variance of the sample means will be the original variance of the data divided by my sample size. So what if the original variable isn't normally distributed? All right. Well, we don't really care because we have this thing called the central limit theorem, which as long as we have a sample size over 30, then we know that the sample mean distribution will be approximately a normal distribution. Okay. So even if I start out and X is like uniformly distributed, if I take samples over size 30, I know the sample means will be approximately normally distributed. Okay. So let me see, here's the kind of, yeah, here's a nice little visual. All these, none of these start out as a normal distribution, right? These are 4 different distributions. Here's a uniform. The others are nothing we've even talked about. Even when I get to samples of size 2, these things start to look, the sample mean distribution starts to look a little bit different. Then when I get to samples of size 6 even, well, maybe there's a, this looks pretty normally distributed. This is a little skewed. This might be skewed. This looks like it's kind of looking like a normal distribution. By the time I get to 30, none of these distributions are skewed. They're symmetric, and they're all centered around wherever the original mean of the data that we sampled from was. Okay? So it doesn't matter what the original variable looks like. If we get to a sample of size 30 or more, our sample means will have a normal distribution, and the mean of those sample means will be whatever the original mean of the data was, and the variance will be the original variance divided by our sample size. So we'll pick up with this example next class, where I basically show you some population data. I then do a bunch of simulations where we take like 1,000 different samples and can kind of prove that what I'm saying is true. It doesn't matter what the original variable starts out as. Once we take samples over size 30, those sample means will be normally distributed, and their mean, the mean of the sample means, will be whatever the original population mean was, and the variance of our sample means will be the original variance divided by our sample size. So I'll walk through that data exercise with you next class. We'll start to work on some problems, finding the probability I see a sample mean above or below a certain value, and relate this to what we were talking about kind of prior to today's class. Okay. All right, start working on that Connect assignment so you can get some of those questions to me out of the way as soon as possible. I'll put an online quiz up today that'll be due before we start class on Thursday. Other than that, reach out to me via email if you have any questions, and enjoy the rest of this beautiful day.